We'll start talking about the respiratory system now. We inspire, we bring air into our lungs through the nasal cavities, and we humidify air and we filter air, warm air, and then the air goes down to our pharynx and then down into the larynx and then down into the trachea. And it's then branches off to the left and the right lung through the bronchi. And the bronchi further divide into smaller branches, the bronchioles, with the most terminal portion of the lungs being the alveoli, which are the small air sacs where we have oxygen and carbon dioxide exchange into the blood. When we talk about pulmonary ventilation, we're referring to moving air in and out of our lungs. And pulmonary diffusion is the exchange of oxygen and carbon dioxide from the blood to the alveoli for CO2, and then from the alveoli to the capillaries or into the capillary bed in the lungs with oxygen. We can also talk about it at the in the muscle bed, where we have pulmonary diffusion, where we exchange oxygen and carbon dioxide. Oxygen is transported via the blood by binding with hemoglobin, and there again, it's at the capillary level where we have this exchange of gases with oxygen and carbon dioxide. When we talk about respiration, the ability to move air, ventilation, moving air in and out of our lungs, air moves from an area of higher pressure to an area of lower pressure. And to accomplish this, we have, when we inspire or bring air into our lungs, the diaphragm, which is a dome-shaped muscle in our abdomen, pulls down, and at the same time, the external intercostal muscles, they expand the rib cage and they pull the sternum up and out, and that stretches the lungs and makes a larger cavity, thoracic cavity, and so we have decreased air pressure. And so the air will move from an area of higher pressure out in the environmental air into our lungs, which is an area then of lower pressure. And then to expire or release air from our lungs, it's more a system of a passive recoil, where the muscles relax and the ribs return to their normal resting position, and the diaphragm raises up and pushes the air out of the lungs. And so there again, the inspiration is accomplished by muscles on our in our ribs and our diaphragm. And when we're exercising, we also get additional help from other muscles like in our neck, on our rib cage, that allow us to expand our ribs even more so. And expiration, again, being more this passive recoil or relaxation of the muscles that allows the rib cage to return to its normal position and forcibly force the air out of the lungs. So we have, when we look at the capacity of our lungs to bring air in and out of our lungs, we have different things that we measure. And one thing is our tidal volume, which is the normal inspiration and expiration. So it's the normal breath that we take. And then we also have an inspiratory capacity. We have the ability to go beyond our tidal volume or our normal inspiration and take more air in. And we also have the ability to expire or force more air out of our lungs, an additional expiratory volume. And when we take our normal tidal volume, our normal breaths, and we add to that our inspiratory volume and our expiratory volume, we have what's called our vital capacity. So that's the ability to maximize our inspiration and our expiration. And residual volume is the amount of oxygen that remains in our lungs even after we forcibly exhale. So pulmonary ventilation, or we call minute ventilation, is our tidal volume, or how much air we breathe in and out, times our breathing rate. When we look at our blood, we know that our blood transports oxygen. We see that we have plasma, which is a liquid portion of our blood, which is by far mostly comprised of water. And then we have our formed elements, which are our red blood cells, our white blood cells, and our platelets. And the majority of it is our red blood cells, which transport the oxygen. So we call our white blood cells leukocytes, they fight infection. Our platelets are for clotting, and our erythrocytes are our red blood cells, and they transport oxygen by using hemoglobin. So oxygen transport is accomplished by the red blood cells containing hemoglobin. Each hemoglobin can carry 4 molecules of oxygen. And most of the time our blood is almost fully saturated with oxygen. The hemoglobin does bind to its total capacity. About 2% of the oxygen is dissolved in our blood, and then the rest, 98%, is transported through this hemoglobin. And a gas exchange occurs at the alveoli, and the alveoli are these little air sacs that draws the oxygen into the air sacs, and then a network of capillaries surrounds the alveoli, and it's a very thin wall that allows for gas exchange. And gas exchange is accomplished through, we look at what's called an oxygen hemoglobin dissociation curve. And that is accomplished by, there again, areas of high pressure, gases moving from an area of high pressure to low pressure. And when we look at oxygen, we refer to what's called the partial pressure. And that just means of the air pressure, how much responsibility of the total pressure is due to oxygen, because our air is a mixture of nitrogen and oxygen and carbon dioxide. And so the partial pressure is how much of that total air pressure is oxygen. And it takes on what's called a sigmoidal or S-shaped relationship, which is a relationship between how much partial pressure, how much pressure is exerted by oxygen, causing the hemoglobin to be saturated with oxygen. And I'll show you in the next slide the curve. But we have something also called cooperative binding, and that just means once one molecule of oxygen is bound to hemoglobin, the remaining oxygen have a greater affinity or attraction to hemoglobin, and so they will more readily bind with the hemoglobin. And so this is the oxygen hemoglobin curve, and it just shows you that at higher pressures, at higher partial pressures of oxygen, there's going to be more saturation, more binding of oxygen to hemoglobin. And this is what we're going to see more in the lungs. And then in the tissue is the more steep curve, and that's where we see what's called dissociation, where we see oxygen released from hemoglobin. And so the flat part of the curve just shows us that even though we have much greater increases in the partial pressure of oxygen, it really doesn't change the oxygen saturation that much. So what that allows us is, even if we have some decrease in the saturation of oxygen in the lungs, we're still going to be pretty saturated and be able to carry, the blood's going to be able to carry a lot of oxygen. And then the sharp rise is more what's happening at the cellular level. And that just shows us even when we have very small changes in the partial pressure, we're going to have big changes in the release of oxygen. And that's what we want, because we want in the lungs oxygen binding with hemoglobin regardless of these changes in partial pressure. But we want to see the hemoglobin releasing the oxygen in the muscle bed easily. And so we can see a shift in this oxyhemoglobin saturation curve. And what it means is if it shifts to the right, it just means that it's the hemoglobin is going to be more apt to release oxygen. And then if the curve shifts to the left, it's more apt to have a greater affinity, or the hemoglobin is going to hold on to the oxygen more readily. And so there's things that cause this shift in the curve. And one of the things is increased carbon dioxide production, which occurs in the muscle with cellular metabolism. And then we're also going to see a shift to the right where we're going to have a greater release of oxygen from the hemoglobin when we have an increase at acidity. So that's when more hydrogen ions are produced. And then exercise generally increases the release of oxygen from hemoglobin as well as increased temperatures. So you can see how when people exercise, they do generally increase carbon dioxide. The muscle becomes more acidic and the temperature rises, and all of that results in a greater release of oxygen. And this greater release of oxygen is needed to fuel exercise to produce more ATP in the presence of oxygen. So there again, shift to the right just will mean that the oxygen the hemoglobin has a less of an affinity for oxygen, so it's going to release more oxygen into the muscle. And then if we shift to the left, the hemoglobin is going to hold on to the oxygen greater.